Hi everyone. So thanks for coming to my talk about basically how do we find interesting features, especially interesting scientific features, or as I like to call it, interesting features and where to find them. So hi, I'm Dan. I've been a data scientist and researcher in the industry for a decade now. These days I also do a PhD in my spare time, specifically about how to find interesting things in data in lots of domains, lots of ways. Everything from biological models, healthcare, tabular time series, proteins, viruses, churn, you name it. There's also a decent chance I took your photo at some previous data hack. So we'll be going over just what are interesting things and why we should even care about them, a little bit about how the approach I did here works, and what's in it for you and how you can use it. Also, if I speak too fast, somebody throw a paper at me. I tend to do it that. So why do we care about things which are interesting? So pretty much any data science problem, which is not very simple deep learning stuff, you're going to have at some point a great big pile of features. Even if you have a great platform, great setup, feature store, warehouse, AutoML, you're still going to have a great big list of features, maybe ranked by statistical power, lift, direction, whatever. It's still a huge pile of lots and lots and lots of features that you need to look at. And in a lot of use cases, especially if you're a data scientist, that you need to understand and to get insights from. What do we need to do with this? What are we going to do with this? Do we change our processes? How do we identify churn? Who's going to get sick? What are the things we didn't know were risk factors? You name it. So basically, you're going to always have a huge pile of features, and that's pretty much a bottleneck. In some cases, you can figure it out yourself, but in many cases and many domains, we need an external expert. You might know a fair amount about biology and medicine, but, well, people who take this medication while they're undergoing that type of cancer treatment with this type of immunotherapy at that type of stage, it's like, okay, is that because of the billing process, or is it because people who are taking that drug are going to have an overdose from opium? How do you know? You need to ask an expert, and experts are rare and expensive, and it's hard to get their time, even when money is not a problem. And usually it is a problem, and usually their time is much more of a limiting factor. It might be the CEO of your company, and it might be a medical expert whose every hour is $500 or $2,000, and only has a few hours in a week when they're not working on kids with cancer. So this is a very limited resource. And what we'd ideally like is, instead of saying, well, we have the top 300 features, 100 features, and what's actually relevant here, what's nonsense, what is happening just because, oh, turns out this is because I changed the insurance policies in 2015, we'd like to say, what are the relatively relevant stuff, and let's get the insights about that. So I'll also note, I'm not talking about replacing the humans in the loop. In my opinion, we're never going to replace humans, but we can do a lot better than just, here's a huge list of results. Think about Google and search. You're not going to get, your top search result is not always right, but it's a hell of a lot better than just going randomly through papers or results or searches. And the goal is to get your insights with much, much, much less time and cost, no matter the project or problem. And preferably while sacrificing as few goats as possible for said data. So what makes something interesting? So one of the problems, especially if you're trying to write a paper in the field, is that there's no decent citable formal definition of what's something interesting, except for, oh, of course it's interesting, I know it when I see it, which works sometimes, not so much for the rest of the time, and especially if you want to do anything formal or rigorous. What's something more interesting? What's something which is statistically meaningful and important? Great p-value under 0.05, aka only a 1 in 20 chance of it being random, or 1 in 1,000 chance, 1 in a million, 1 in a billion, 6 sigma, yada, yada, yada. So that's fine and great, but we're not talking about statistical significance, we're talking about what is something interesting. If I see one person who can fly by flapping their hands, that's very, very interesting, even though the p-value is zilch. And understanding whether something is important is, well, hard. How do we define it? Well, is it something because it's original, it's good, is it important? What is important? We end up with a bit of a tautology in defining it, beyond saying, well, it's interesting and important and mysterious. So in this work, which I'll note had a lot of reliance on some previous stuff we've done with creativity and humor, if anyone wants to see a sneak talk of humor about Cards Against Humanity, we came up for 3 different pillars about what's to help define something as being interesting. Number one, which I will admit it's a huge bias towards anything involving scientific research. In industry, you might not care about this anywhere near as much, is it novel? If I were to, when I see this, did I already know about it? Is it trivial? Is it obvious? So, of course, this depends. Does anyone else in the world know this? Is different from, do most people know this? If I were to say, hey, did you know that eating onions reduces your risk of such and such, then if you're a doctor in the field, you might know it. And in other cases, you might not know it, depending on the problem and the domain. If I were to say, hey, did you know smoking causes lung cancer? Boring and trivial. Did you know that we found a whole new cancer, smoking increases its risk? Probably not interesting because smoking is bad for a huge amount of stuff, but it still might be novel. How much, to what degree, but we're getting there. If we're talking about, say, smoking reduces your risk for certain autoimmune diseases, that can be novel and interesting. By the way, I'm not saying for which diseases, and don't smoke. Smoking is terrible. PSA of the day. So second bit is utility or usefulness. End of the day, if we can't get anything out of it, then we don't care. If I were to say, hey, did you know that eating apples gives you a lower risk of cancer? You would say, oh, yay, by how much? But by 1 in a trillion. So, okay. And also, not even 1 in a trillion, but hey, I said that maybe eating apples reduces your risk of cancer. Then, if it doesn't even have an effect, then we really don't care. So again, doctors washing hands was found to reduce the deaths in childbirth by more than 90%. This was found, by the way, in the mid-19th century and was completely ignored. The doctor who found and proved it was tossed out in the street and laughed at because this was so completely ridiculous. And we got another century and a half of having about 20% chance of childhood mortality. Why did this happen? Because it's not enough for something also to be useful and to have an effect. It needs to be plausible. Plausibility is basically saying, do I have an explanation or mechanism for it? So this is a problem if you've discovered something completely new, in which case, good luck and enjoy the Nobel Prize if you manage to get it through. But in general, for something to be interesting, we also need to it needs to make sense, to have an explanation, explanatory mechanism. A way I like to think about it a lot is, would I feel embarrassed presenting this now to the C-level executives at a company? If I can explain it to them, then it's all right. It might be something incredibly ridiculous, but hey, did you know that buying these type of things helps us identify pregnant women, which is super valuable? Why? Because they also get craving for chocolate before the blah, 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 blah. And we can show it and explain it, and okay, they guess buying Pampers and chocolates is a sign. And again, think about theory of gravity. Small things are attracted to bigger things. Makes sense why apples fall off trees. Lots of work from there. On the other hand, saying that you should invest in real estate in Salt Lake City because the angel Mormoni told me will probably not go over very well with BlackRock. So for something to be interesting, it should be novel, it should have an effect, be useful, and should make sense to some degree. Hopefully, any arguments? Great, none. Okay, so how do we get to this with the Interfeat pipeline or approach? Interfeat, interesting features. Not the best name, but. So, in short, take your bunch of features. Is it useful? Is it novel? And also use a language model or LLM to help get the plausible explanations and for some re-ranking. Mix it around, get the shortlist. There you go. So, input again, bunch of features. By the way, I'm talking specifically about tabular data, but it can be anything. Like a time series, you can get it as features. Free text, what are the words? What are the combinations? What are the effects? Deep learning models, whatever. Filter it by utility, which basically means keep features with a predictive signal. Novelty, drop the stuff we know already. And AI LLM, get the explanations and also some fun re-ranking. So the data set we used in this work is one called the UK Biobank. Anyone who's worked with biomedical might know it. It's about 400,000 people and all of their medical data. Their medical records, their history, their diet, their exercise. Do they drink coffee? Do they drink tea? Do they eat lamb? Do they eat pig? How often do they eat it? When were they diagnosed with various diseases at different ages? All of it, even their genetics and imaging data. Big, big, big data set. And very rich data set. And also one where there's a lot of work because there's a lot of stuff that we didn't know. By the way, for example, do drinking hot drinks increase your risk of esophageal cancer? So out of this, we took a bunch of different diseases. Basically, we take the people's data at around 2014 when they were registered in the data bank. We have their medical records from later on and see were they diagnosed with some disease within the next 10 or so years. In other words, future prediction of diagnosis with a disease, given a few thousand features, not counting the free text. Thousands of columns, plus columns of free text, which were, again, features extracted, stuff like disease, medications, the other diseases, codes, age of onset, you name it. Like I said, a lot of features. By the way, we made a bunch of code for getting the features out of it and making them human readable, which is much more painful than you would think, especially for free text. So, how do we do the filtering? Step one, utility. We want, in machine learning, we'll say, well, does a feature have any predictive power? So, as anyone who's done machine learning knows, what's predictive power is a lot trickier than it sounds. So, we go for a high recall approach where basically drop the stuff which has zero signal and keep the stuff with at least some degree of signal. I'm not looking for the optimal best top 3 features model. I'm looking for get rid of the stuff which has no signal at all, toss it out, kill it, and keep the stuff which maybe has a signal, we can dig into it later. I don't want to lose the very interesting features. What do I mean by that? So we keep any features which either have a signal based around classical p-value, t-test, correlation, yada yada. P-value better than 0.1. By the way, if you look in literature, you'll see stuff as 0.2 for a lot of interesting things. 0.1, not 0.01, by the way. This is like very liberal. Or we'll keep any stuff with mutual information. Mutual information meaning I can get a signal like, is the age extremely young or extremely old? Relatively nonlinear. I'll also keep anything which has Shapley value. We train machine learning models on all of these tasks. So again, I can keep anything which has stuff like BMI. Age and height does not tell you if you're obese. Height and weight does not tell you if you're obese. But if you are height divided by weight, then you can get that. So again, basically keep a short set of features which have some degree of statistical significance or predictive importance. That gets rid of a lot of the junk, but we still have a lot more. So next step is looking at novelty. So we use 2 completely separate steps to basically try to get rid of the really obvious stuff. And note again here, there's a lot of noise in this process. Our inputs are all of the different features, and a feature can be pretty complicated. That said, we use 2 approaches, one being a knowledge graph pass, and the second one, a literature pass. What does it mean? So I'll go into each one in detail, but in short, do you appear in the knowledge graph as linked, and do you appear in the literature a lot as linked? Another minus about this step is we're ignoring directionality. Smoking causing cancer is boring. So if we were to find smoking reduces disease risk, that can be interesting. But how do we find this approach kind of ignores that. But it's a good way for getting rid of stuff like, smoking causes disease, or age increases is a mortality rate. So for the knowledge graph, we took a very large, knowledge graphs are basically, here's a bunch of entities, here's the same bunch of entities, what are the relations between them? For example, Obama, born in USA. And in this case, the entity of disease smoking has a relationship of affects lung cancer. And smoking is a disease. So this is around 140 million or 80 million or so relationships. It's all extracted out of the very large biomedical data set called PubMed, basically pretty much all of the literature and notes. It also has a very good rule-based parsing and extraction, so it's pretty clean, and we can filter it for evidence, which is also pretty important. If something appeared only once, I don't care. If something appeared in at least 4 completely different papers, good enough for me. So we have a huge knowledge graph with all of the entities and their relationships. So what we do is we take a library called SciSpacey. This is based around the Spacey NLP library, and basically do some named entity recognition and linking. I get the entities which I can link to any given feature, top 3 specifically. I take the disease or the target and get the top 3 entities, link them into the knowledge graph, and see if I have any type of direct link between them. By the way, again, here, high blood pressure is an example feature. So the top 3 features might be hypertension, systemic arterial pressure, and blood pressure. Note again, blood pressure is the 3rd highest, and this is a very, very easy one. Think about something like systemic diastolic liver, whatever. So again, the linkage part, I'll note it's hard and it's noisy and there's a huge amount of manual code here. For example, getting stuff like entities which appear very frequently. TF-IDF is a nice trick for that. You will always need to do manual work on this type of step. Something which I added here, which is very non-standard, is using a little bit of language modeling, specifically a BERT style encoder model, and we just looked at all of the extracted size-spacey linkages, or again, here is a feature, here is its entities, and filter based around the cosine similarity there. So the advantage here is that we can look at the sentence of a feature, because the named entity linkage is extracting tokens or part of phrases, and it can miss out things like high blood pressure. It might get high and blood pressure, but the sentence is high blood pressure. Never mind a feature which might be 5 or 10 words, like age of onset of disease, Alzheimer's disease, early onset syndrome. That's a lot of words and a lot of places for a linkage model to mess up. So also I'll note we used BioLord. It's a domain-specific language model, and in these cases, I evaluated a bit. It did a lot better than much, much larger non-specialized models. So look at your domain in general, unless you're doing easier stuff, in which just use modern BERT. So basically, we have our entities, features, targets. There's a direct link in the knowledge graph. If there is, with high confidence, then toss it out. It's boring. We don't care about smoking causing cancer. Second separate step was using the literature. So you can basically use anything you want for this. You could use Google search. They have a custom search API. It just costs you a couple of cents for every search, which is annoying if you don't have a budget. What we did was use PubMed, again, huge knowledge base of pretty much all of the biomedical literature, with a free API, with search term expansion, which is really important in some domains. And basically, how many results do we have in the literature for the target, for the feature, and for cases where the feature appears together with the target. If we have pretty much no hits for any one of these, then okay, ignore it. And when I say ignore it, I mean let it pass on. If we do have hits and we see many appearances of the feature together with the target, then let's do a simple statistical test. Do they co-appear more than we would expect by random? If something appears 10 million times in literature, then we would expect it to appear with something else 1,000 times. If it appears 10 million times and the other thing also appears 5 million times together with it, probably not by coincidence. So again, relatively liberal test, but we just want to see, does it co-occur significantly? If not, let it pass. If I can't have an answer about it, then that's okay. We want high recall here. We want to get rid of the really stupid stuff. You want to get rid of the whole, hey, did you know that customers who have been with us a long time are less likely to churn? We know nobody cares about that. You want to get rid of the stupid stuff which is going to waste your time. Finally, AI, LLMs. Woo, well, boo. I really don't like LLMs. So we took all of the results which have been passed to this step. By the way, the previous steps, some of them on offline, some of them online, but they're still very fast and cheap. LLMs cost more. They're not that expensive, but if you're in academia, they are, and also takes you time to run the prompts. So here we took an LLM. We made a very long, very detailed prompt for each part of this, but basically you are an LLM, blah, 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 researching this topic and problem, given insert feature name here, and its relationship with insert target here. And criteria, is it novel? Another one, blah, blah, blah. Is it plausible? Another one, blah, blah, blah. Is it interesting overall? So we take that and we have it output a score. We also, by the way, this isn't technically RAG, this is using evidence and the snippets of text which are related to the feature or to the target from the literature. I used BM25 for this because ain't nobody got time to start indexing about 100 to 100 million documents. It's a lot. People can do it. It's not great ROI. BM25, TF-IDF is much faster. So, okay, I'm good. Yeah, good with time. So basically, this is kind of how it looks. Given the feature, blah, 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 and the explanation from an LLM for that stuff. Again, this is using a pretty cheap LLM, and we get also numbers. I'll also note this worked pretty well with free LLMs, which I also used in the debugging 3 billion sized models. But in the end, we used OpenAI, if only because they support structured outputs, which means you can get the output in a JSON and say, give me the output for this thing as a number. And that's really good if you're trying to do benchmarks and evaluation and don't want to go over it by hand. Here's my 500 features, give me the results. We also had another option of using an additional set of re-ranking of everything at once with O3. We didn't do it in the first place because O3 did not exist when I was doing the work. And also, it's very manual. But again, this is very, very, very cheap in terms token-wise for anyone who's scared about it. So, results. So, in general, start with, technically this has a lot more than 3,000, but just the utility feature, you're looking down to a few hundred, and each step cuts some more. In the end, we had around 50 candidates for each feature and target. By the way, different number of candidates for each disease. It's not 50 for every single one. That would be very suspicious and very strange. One evaluation we did was to see whether the approach worked at all. Here's all of our features from 2011. Here are all the features after just the utility feature. How many of those are known in the knowledge graph at the time? Knowledge graph, again, gold standard literature. How many of those will appear by 2024? At least 20% popped up again by 2024, i.e. we found at least 20% of those with about up to 14 years in advance of the literature. And again, this is a database was available before that, and these are very well-studied diseases. So that's quite a lot, especially if you didn't know about some of the risk factors. So basically, long story short, approach works for finding novel links in advance. Yay. But that's not the interesting question. The question is, how do humans like it? So for here we did human evaluation. And very, very expensive humans. We took 4 very senior medical doctors who were also professors, all research MD doctors, also with experience with these diseases, and gave them the candidates for the different diseases. And one thing we also did, by the way, over these candidates was give them a bunch of fake distractors. We took a bunch of features which had zero utility, basically made nonsense, and didn't tell the doctors about it, and to see if whether the doctors could tell the nonsensical stuff apart from the real stuff. So again, they got the feature, the target, how does it look, and please tell us how interesting, novel, plausible, blah, blah, blah you think it is from 1 to 4. They also like the LLM explanations, by the way. So overall, they found about a third to be interesting, which to my mind is pretty darn nice, although depends how you look at it. They also easily spotted the fake distractors, which is kind of surprising, honestly. I mean, the distractors can be, I would not be able to guess, hey, did you know high vitamin D, is it a distractor or not? Good luck guessing. The LLM matched somewhat with the doctors. Utility, yes. The lowest was actually with how novel something was, where interestingly enough, the doctors found stuff to be way more novel than the LLM. So the LLMs actually did not hallucinate enough. It was more skeptical than the actual doctors, which is interesting. And another baseline we also did was to say, what did the average data scientist do in the field? Well, if you're a good data scientist, so if you're a statistician, you might rank by p-value or log odds. If you're a data scientist, Shapley values. Long story short, train a model. What's the overall predictive importance of each feature? This is not the full explanation, but I'm low on time. And it also helps us see stuff about collinearity of features, multivariates, and so on. I'll note, by the way, our feature selection approach does a lot of stuff behind the scenes, but no time for that. So, how well does our approach do versus SHAP? And another question we wanted was, how well does it do if we snipped off some parts of the pipeline without the LLM or without some parts of the novelty selection pipeline, which again, it's complexity, it's overhead. So we basically took the top 15 features by the normal pipeline and the pipeline without different components and by SHAP and sent it back for annotation. So using the SHAP, you can't see it because it's a 0 here out of 15. And basically, more steps, better results. And the LLM helps between somewhat to a lot. So basically, interesting is not the same as important. Telling about someone that they're at high risk of heart attack because they are 85 and weigh 200 kilos it's important, but it's not very interesting. Telling them that they have also a higher risk because, hey, did you know that if you eat 20 onions a day, it will reduce your risk by such and such? More interesting. By the way, there was no feature with onions, just to be clear. The medical disclaimer. But yeah, interesting is not the same as important, and especially for some of these problems where we're doing research. We want to find things which we can act on or analyze more, and some features will only have an effect if we dig into them. If you eat 1 apple, maybe no effect. If you eat 10,000 apples or 10,000 grams of vitamin D, maybe will have an effect, and you just don't have it in the data, but you can pick it up. So some of the stuff we got was, for example, in esophagus cancer, which is a painful topic for me, was stuff about genetic risks for other diseases, melanoma, arthritis, lupus, stuff about inflammatory processes. Ovarian cancer risk had the opposite effect. and higher risk for ovarian cancer, lower risk for cervical cancer. I'll note all of the data here is also controlling for age, gender, and BMI. We had a fun inverse propensity weighting model which I built for this. No time to go into it, but it really helps also get rid of the noise. And you should do it in your own analysis also. And also asthma sucks genetically. Also, yay, chance to mention house and lupus. Another one was, for example, heart attacks, where we found that stuff like, say, long-term childhood antibiotic use increased risk, which is, actually we have another study going on with another group where it's also they were really surprised that we mentioned that because they were planning to do an entire project to ask this question. So, pretty nice to find this out in advance. Also stuff like, say, anxiety and panic attacks increasing your risk, but people with PTSD had lower risk. Why? Need to dig into it. It also might be because of medications, might be other things. This is not causal, but it's, hey, this is not obvious, this is not trivial. There's way more examples in the paper, obviously, but we're not going to go into that. But basically, we're finding risk, which, again, to a person who has been studying this for many years, was going, hey, that's really interesting, and like, yeah, I would like to study that. So, overall, you're going from thousands of features to dozens. And then again, this is a pretty complex pipeline. In other cases, you might have way less to analyze. You're spending way less time of your experts, very, very expensive time, and very limited. And also the approach generally works for finding features in advance. You're not getting nonsense stuff. Overall for you, so all of the stuff here is in code and it's highly modular. You can run each step separately. You can modify it for your own uses and you can apply it to any domain. You don't need to search PubMed. You can search Google. You don't need to use the knowledge graph. You can use your own knowledge graph or you can skip it. Honestly, you can just use only the LLM, but you want to look at the prompts and to have some idea and maybe a much higher budget. LLMs over 10,000 pairs is a bit trickier. And again, all of the code is available. Other people have run it, including one lab which started using it just before they got bombed by Iranians, which I'm sure won't happen to you. So the paper is also online along with all of the code. Welcome to read it. Welcome to cite it. And yeah, thank you very much. And questions?